Hello everyone. Welcome back. Let me start with a thought. Why don't bridges collapse under their own weight? Or why doesn't a skyscraper lean like the Tower of Pisa every time the wind blows? The secret superhero here is elasticity. Engineers rely on elastic behavior every day, from cranes lifting cars to beams holding up towers. If we didn't understand elasticity, we'd be building houses of cards, not homes and skyscrapers. Now imagine a crane lifting 10,000 kilograms. The big question, how thick should the steel rope be so it doesn't snap? The condition is, area A must be greater than or equal to weight times G divided by yield stress. A is greater than or equal to open bracket M times G close bracket divided by sigma sub y. Where M is the mass, G is acceleration due to gravity, and sigma sub y is the yield stress. Substitute values. M equals 1 times 10 to the power 4 kilograms. G equals 9.8 meters per second squared. Sigma sub y equals 3 times 10 to the power 8 pascals. So A is greater than or equal to open bracket 10 to the power 4 times 9.8 close bracket divided by 3 times 10 to the power 8. That gives 3.3 times 10 to the power minus 4 square meters, which corresponds to a radius of about 1 centimeter. But engineers love safety. With a factor of 10, the rope radius is about 3 centimeters. That's why real ropes look chunky. Let's now talk about beams, the backbone of bridges. When a beam is loaded at the center, it bends or sags. The sag is called deflection delta. The formula is delta equals W times L cube divided by open bracket 4 times B times D cube times Y close bracket. Delta equals W times L to the power 3 divided by 4 times B times D to the power 3 times Y. Here W is the applied load, L is the span length, B is the breadth, D is the depth, and Y is Young's modulus. Notice something cool, depth comes with a cube. Increase D just a little and bending reduces dramatically. That's why beams are made deeper rather than just wider. Here's a design puzzle. Why are beams often shaped like the capital letter I instead of being just solid rectangles? Rectangular beams buckle easily and thin beams bend like noodles. But the I section is magical. It keeps material at the top and bottom, where stress is maximum, and removes unnecessary material from the middle. So you get strength without extra weight. And yes, you also save cost. That's why modern bridges and skyscrapers are filled with I-shaped beams. Now, think of ancient temples or modern buildings with tall pillars. Why are the ends flared or distributed instead of plain flat? If the ends are narrow, the load concentrates, increasing stress. But with wider ends, the load spreads evenly. Look at figure 8.8 in your book, a pillar with rounded ends versus one with distributed ends. The distributed one clearly supports more load safely. That's why architectural design often looks stylish and scientific at the same time. Now let's move from man-made structures to nature. Did you know mountains also follow elasticity rules? Why don't they grow endlessly tall? At the base of a mountain, stress equals H times rho times G. Stress equals H times density rho times acceleration due to gravity G. The elastic limit for rocks is about 3 times 10 to the power 7 pascals. Density rho is about 3 times 10 to the power 3 kilograms per cubic meter. G is about 10 meters per second squared. So set sigma equal to H times rho times G, rearranging, height H equals sigma divided by rho times G, that is 3 times 10 to the power 7 divided by open bracket 3 times 10 to the power 3 times 10 close bracket, which equals 10,000 meters or 10 kilometers. Let's solve step by step for practice. Given mass equals 10 to the power 4 kilograms. G equals 9.8 meters per second squared. Yield stress sigma y equals 3 times 10 to the power 8 pascals. Formula: A is greater than or equal to mg divided by sigma y. Substitute: A is greater than or equal to open bracket 1 times 10 to the power 4 times 9.8 close bracket divided by 3 times 10 to the power 8. That gives 3.3 times 10 to the power minus 4 square meters. Radius r equals square root of a divided by pi. So r equals square root of 3.3 times 10 to the power minus 4 divided by 3.14. That is about 0.01 meters or 1 centimeter. With a safety factor of 10, radius equals 3 centimeters. Engineers always go bigger to avoid disaster. So, let's wrap this up. Elasticity is not just classroom math, it's what makes the world stand strong. We saw rope thickness depends on yield stress. Beam bending reduces drastically with depth, and dissections are the champions of design. Columns with distributed ends spread stress safely. Mountains have a maximum height of about 10 kilometers thanks to rock elasticity. Elasticity is the invisible architect, shaping our buildings, bridges, ropes, and even the tallest mountains. I hope you now see elasticity as both an engineer's tool and nature's law. See you in the next class with another fascinating journey through physics.